Hello everyone, welcome back to my channel. In this video I will show you how to calculate Phonon density of state of silicon crystal. And I have already pasted the reference spectrum here, where the x-axis is the frequency and y-axis is the density of state of phonon. Okay, and in this video I will walk you through the steps to do the calculation and also the input file one by one, but I will not really do the calculation because it takes a lot of time and yeah. Okay, so the first step is basically the same thing as last video, that you need to do a self-consistency calculation using pw.x. Yeah, and the input file is also the same as last time. I decrease the convergence threshold for the electrons to make it more precise for phonons, and I also set the offset to be a half a Brillouin zone, so this will help a little bit for not so dense K points. Yeah, you can also set it back to be 0, 0, 0. Okay, so after this calculation, we use also similar as last time, we use ph.x to calculate the dynamical matrices in the reciprocal space. Yeah, and this is the input file, and the first line is just the title line. You can write whatever you want. This will not be calculated, and in this name card you need to keep the output directory and also the prefix the same as when you did the self-consistency calculations. So basically you need to keep the output directory and prefix consistent in the whole calculation. And this is the phonon convergence threshold, and the lower you set it to be, the more precise the calculation would be. And this LDisp means that you will calculate the phonon frequencies on a grid of Q points, and those NQ1, NQ2, NQ3 specifies the Q grid, which is the 4x4x4 grid. And this is the atomic mass. You can also leave it out so that it will use the same value from the self-consistency calculation. And now in this video this is important, because this is the output file that contains the dynamical matrix, and this would contains the data that is needed in the next step. Yeah, okay. And then the third step is basically do a Fourier transform from the reciprocal space in the last step to the real space. Yeah, and for that you will use the program in Quantum Espresso called q2r.x. and the input file is here. And it needs the data from the last step, and it outputs a file called this one, and this would be the input file of the next step. Yeah, and this is the sum rule. You can set it to be default, that is none, or you set it to be simple. You can try around, but the important information is that you have to specify this to be the same as the one that is in the last step. Yeah, okay. And then in the next step 4, you use this program mat.dyn.x to calculate the phonon frequency at any given list of Q vectors. So in this step you can either calculate the phonon frequency for a uniform grid of Q vectors and give you phonon density of state, or you calculate the phonon frequency at like on a specific path, and then that will give you the phonon dispersion, which I will do in the next video. Okay, and the input file for that looks like this. So if you want to calculate density of state, you need to set density of state equals true, so the calculation would be a density of state calculation. and also this is the atomic mass, and this is the data file that that is generated in the last step. You remember here. So those two lines should be consistent, and then the this program will output the tensor state file that will contains the actual tensor state. Yeah, and then this is the K points or the Q points, Q grid that is that consists of 50 by 50 by 50 Q points. So it is a very dense grid, because for the calculation of tensor state, you need to perform this calculation on a dense grid, and this will take some time. Okay, and then in the last step, we will use GNU plot to actually plot the tensor state. So I will just show you the output. If you just run the step 1 to step 4, the output would look like this. Yeah, I will not walk through all of them, but just remember that the final output is what you defined here. Yeah, so this is the tensor state, and we will look for this file, that is silicon.phdos. Yeah, you will see this tensor state file contains 4 columns. So the first column is the frequency, the second column is the tensor state, the third and fourth column are partial tensor state. So you see that they are identical, and the tensor state is just the sum of the 2 partial tensor state. I guess the partial tensor state is the partial tensor state of atom 1 and atom 2 in the lattice, because we have 2 atoms in the unit cell. But what you need to do is to plot the second column against the against the first column, and that will give you the Phonon tensor state of silicon. Yeah. So we can actually do that, and we use GNU plot silicon.5. Okay, I haven't shown you what this file is about. So this file, basically it plots the data in the data file, in this silicon.phdos file, using the first 2 columns. Yeah, so plot the second column against the first column, and with the title and line points. Yeah. Okay, so then I will just do just plot it, and you will see that actually the x-axis is the frequency, y-axis is the tensor state, and I will just take a screenshot. And put it in the Excel. Okay, to compare. So I will make it a little bit smaller. Okay. Yes, and you see calculated, and you see that it is very similar as the reference. Here, the peak structure and also the peak position and also the frequency and everything is the same. Okay, so in this tutorial I have shown you how to calculate Phonon tensor state, and you can find my code in the GitHub, so that you can run it yourself. And if you like my video, please press like or subscribe to my channel, and I thank you for watching. See you next time.